Hello YouTube and welcome to our presentation on a sustainable computational design concept using web surface methods. The paper was submitted to ICED 23 and this was presented earlier this year. And the paper link is down in the description section. So yeah, we started off with saying, we all recognise the impact on CO2 emissions and the rise in global surface temperature and the desperate need for society to reach net zero and reduce our carbon footprint, using renewable energies and designing and manufacturing sustainably. So we've seen that across the board. That's it. Like say using renewable energies such as wind turbine technology and also the design of more carbon neutral products, so such as these shoes here. And fortunately, that's it. If we went to the conference, there was a huge number of podium and discussion sessions on this very challenge of designing sustainable products and doing risk analysis on them, designing for the circular economy there, circular systems as well. So that's it. So much larger systems, not just on the product itself, but this is a system in which it operates. And all of these underpinned all of these are our modelling techniques. We have got such a vast array of complex and advanced modelling techniques available to us, including CFD, finite element analysis, large-scale systems modelling, agent-based modelling, manufacturing production systems modelling, you name it. We've almost got a numerical simulation of it these days. But our question then posed is that actually, how whilst we're designing sustainable products, what about if we look upon ourselves as designers and how sustainable is our design process? And here we've got some examples of the V model, pile and bytes, the stage gate model, and the double diamond. And that's where we pinned what is the how sustainable are these models? And one thing that kind of sparked our curiosity was the F1 2022 rule changes. For those who don't know, there was 16.5 million core hours was spent in the cloud, running advanced simulations to conceptualize and develop the rule changes for the Formula One cars, resulting in over 500,000 gigabytes of data to be stored. And if we looked at, we looked at some of the typical CO2e emissions for cloud computing platforms, and it was estimated that it would be about 14,000 tons of CO2 would be emitted by those core hours running those simulations. And again, that begged us the question, well, do we ever question or do we wonder, is it worth running those simulations, and do we get the value and benefit from running it and making sure that we run the optimum set of simulations for our design problems? And that's why the important reason why is because designing never stops. So even though when we finish our product and that goes out into service, we're continually designing the next product. So continually running more simulations, evaluating much larger design spaces to try and optimize those products to be sustainable. But yes, if we're designing continually, that also needs to be sustainable too. So at the moment though, like you said, for a designer to be computationally designed efficiently, to think about it efficiently, it's all upon the designer himself. So they've got to think about, optimizing the design of simulations, which set of simulations to run, at what fidelity, and which models, which simulation tools to use. Are you choosing the right solvers within those? Because if you don't, you can run more computational time, even though you get the same answers in the end. So picking the right solver for the right problem, and also then exploring the design space in an efficient way. So what elements are critical to model in detail, ones that are not so much detail, how do we navigate that space? And that is tough, for every designer. That ultimately adds work to our process, and requires deep domain knowledge of all of those modeling techniques to make sure that we use them appropriately. And if you look at it, ultimately, it's kind of tangential to the designing the product itself. It's all about configuring and orchestrating a setup to design the product rather than thinking about the design itself. So can we offload that? So that's the other thing, is trying to remove that burden on the designer. And that was our question. So why can't our design process, in a way, self-organize and do it itself? Can we set up simulations in an environment where they can start to become more efficient by themselves? And that's what we've been exploring, and that's what the paper details. So we've been looking to borrow from services such as web service models and web service technologies that efficiently broker, data across networks. So our concept was the idea of creating a gateway broker that is an in-between, a conduit to our simulation models. So you would develop your simulation model, you then potentially containerize it, host it in the cloud. You'd have this broker, which then you can ping effectively design options. You could tell it and request to run a certain set of design options to evaluate. So you could post those details, and the broker would then find the right appropriate physics model in your library and then run that model. But in doing so, and just breaking up that process and having this broker in there, you can introduce the methods of like typical kind of caching mechanisms that you might see in web services. So these could be a simple cache. So if somebody had run that simulation before with the same parameters, you may have cached some of the key results in in a cache on the broker. The broker can then immediately query that. Do we have information on that, and return those results? So we never need to even hit and run another physics-based simulation. We could also put it into databases. And what we were also exploring is the use of machine learning. So rather than just simply caching and hope, and just checking just in case somebody is running a similar model or the model with the same parameters, we were hoping to use machine learning to be able to be that interpolator between existing simulation results, so we can then suggest what the answers would be within a certain level of certainty. And in those requests and response for simulations, designers could set a threshold for certainty. So if they only wanted a rough guess or rough estimate, they might be able to set a low threshold of like maybe an 80% confidence, and the broker would be able to first query the cache mechanism, so be it the machine learning model. If that returns a result with that 80% of certainty, then that will go back to the designer again, never having to run a computationally intensive simulation. If it doesn't meet that simulation that threshold, it would then run that physics-based model, return the result to the designer, but also cache that and also update that machine learning model. So we tested this process out with a simple like 1D heated beam, typically what you see in like you see your typical tutorials for FE simulations or thermofluid simulations. So we're heated at both ends, and we wanted to know what the temperature is in the middle for a given time. And we were able to vary the length and the material. And what we were able to do, what we did was basically effectively perform a typical kind of design process around that. We started with some maybe random exploration of that design space. And every time it would start off initially, we have no data in this machine learning model, it would go to the physics-based model, start to run those simulations. And then over time, the machine learning model would get more confident in certain aspects of the design space and would then take over. So on this figure here, we can see the red points are points when the cache, we call it here, but the machine learning model is responding to the requests of the designer. So we started out with exploration. As we can see, we see a lot of physics-based models being selected by the broker because the machine learning model is not providing the results of the fidelity that we need or the confidence level we needed. But over time, it started becoming more of the red dots, so more of the machine learning model is taking over. So we did that random exploration. It followed a grid search. So you might go, right, I know the area in that design space I want to dive in a bit deeper. I'm just going to run a set of, run the parameters from n to x for a set number of runs, and really like hone in on that space. And actually what we saw there is we saw the cache then taking over very early on, and then maybe at some of this more like limits of the design space, the physics-based model would be selected. And then we did an optimization task. So you've kind of done a few of these exercises in your design process. You're really now going to go, right, I want a real optimum, bar length and material type. And what we did is then, run that optimization task through this broker service. And all the time, the machine learning model was responding with the answers rather than any physics-based model being run. So in the first two steps, we had enough data to have trained that model about that complex system for then it just to start returning results. So our little illustrative example there showed that we could achieve a potentially 25 potential reduction in computational effort. So that's it's 25% of basically the cache mechanism. So the machine learning model, of course, is a lot more efficient to run. We were using an online learning model, so it was learning over time. Every new result, it was learning over time. And then the querying was, it's near instantaneous, so you're not running a massive physics-based model. So if we extrapolated that to the F1 example, that's 3,000 tons CO2 saving just by putting a broker and a caching mechanism in front of our simulation models. And the benefits of learning, we found, because it was an online learning method, so it's learning over time with these new results coming in, we were surprised how early the machine learning model would actually start reporting results with a confidence level high enough. So that was really, really insightful and shows how quickly we could start saving the runtime of using these computationally intensive simulations. And the response time of machine learning models are in the milliseconds rather than the potential hours we would wait for a physics-based model to return. So that in itself as well would add considerable savings in terms of the design process itself. We were able to respond and design more quickly. And most importantly, we're coming back to why we set out to do this, is that the design team would be left to design themselves and not have to worry about necessarily configuring, setting up this environment. Yes, they have to set up the physics-based model, but then that would be hosted on this service, and then they just query that model going forward. So they wouldn't need to necessarily worry about what solvers are being used. So thank you very much for listening. Hope it gives you an interesting flavour of what that paper's about. Please find it. It's in the link, on the description. So for some more links and papers, you can use the QR code there, or just follow these links as well. So thank you very much, YouTube, and see you soon.